Alright, so check this out. What we're going to do here in this investigation, we are going to consider the form f of x equals ax squared. We're dropping the c and the b in this case. We want to see how changing the a actually affects my parabola. So if my function is defined as h of x, that is the function h as it depends on x is equal to 2x squared. If I were to make a table, which I have here, if I were to plug in -2, that would be h of -2 would be 2 times -2 squared. So what I'm doing is I still have that 2, that's where that first 2 comes from, but then the x squared, I basically plug in -2 for x, and I basically figure out what that is. Well, that's equal to 2 times -2 squared, which is actually 4, so that would be 8. So if I plug in x equals -2, I'll get y equals 8. If I plug in x equals -1, that would be 2 times -1 squared, which is also known as 2. If I plug in 0, I'll have 2 times 0 squared, which is also known as 2 times 0, which is also known as 0. And then if I plug in 2 times x equals 1, so this is 2, this is 0. If I plug in x equals 1, I'll have 2 times 1 squared, which is also known as 2. And we kind of expect that to see that because remember, these parabolas, they look the same on the left as the right, so we'll probably guess that that's going to be positive 8 as well. Let me graph that for you. I've got the 0, 0 part over here. What they did was they laid down a f of x equals x squared. This is called the parent function, and basically they're just giving us something to compare it to. Now, 0, 0 is on that graph. 1 comma 2, so I'll go x equals 1, y equals 2, and I'll have 1 or -1 comma 2, so that would be x equals -1, y equals positive 2, and I'll have x equals 2, y equals 8, so that would be 1, 2, 3, 4, 5, 6, 7, 8, and this would also be 8. So the way I kind of look at this guy right here is this is a regular parabola. However, he is still a parabola, but it's kind of like a stretched up parabola. Imagine if I grab here and I grab here and I hold down here and I stretch it vertically. I put it in a stretcher like the torture chamber. You guys ever hear of gummy bears? How do you eat gummy bears? Now be honest with me, the way you eat gummy bears, same way I eat gummy bears, you torture them first. You pull their heads off of their legs and say, please don't hurt me, ah! And you stretch them and stretch them and stretch them, and then you eat them. Well, that's kind of what we're doing with this parabola. When we multiply by 2, we're stretching it vertically. We're pulling the head and the tail in opposite direction, and it makes it skinnier. So this parabola went on the slim fast plan, but actually I kind of like thinking of it as stretching him vertically. Now, if we make it a 1/2 out in front, that makes something different. Let's see how that changes things. In fact, why don't we guess? My guess would be this. If putting a 2 out in front stretches it vertically, then putting a 1/2 out in front will anti-stretch it vertically, or push it vertically, or make it skinny, or not skinnier, but shorter. I basically be crushing my gummy bear in between my hands. So if what is m of -2? Okay, well that's 1/2 times -2 squared, which is known as 1/2 times positive 4, which is also known as 2. So -2 gives me 2. If I plug in -1, I'm going to get positive 1/2. I'll plug in 0, I'll still get 0. I'll get 1/2 over here, and I'll get 2 over here. Graphing that, x equals positive 2, y equals 2. X equals -1, this is 1/2. X equals -2, this is positive 2. Here's what the graph of my parabola looks like. It's still a parabola. I know I kind of drew it more in a V-looking thing, but it's fatter. And I don't want to say fatter. What I'd rather say is shorter. it's kind of like I took the parabola and I took it on the top and I took it on the bottom and I put it inside of a vise that compresses it down. I'll go over to Desmos and try to show you kind of what they look like. Let's go to Desmos graphing calculator. So I graphed y equals x squared. That I call the parent function. But let's graph another one. Let's go 2x squared. So what I did was I kind of took that regular parabola, the red one, and I stretched him vertically. If I make it 3, it will make it an even smaller parabola. 5, even smaller one. Then if I go 1/2, you see how that, you compare the blue parabola to the red parabola. What's happening is you're compressing it. You're making it shorter, which in turn makes it fatter. If you take a gummy bear and you push it between your fingers, it actually makes it fatter. I actually have gummy bears downstairs when I do this demonstration. In fact, I can even make this maybe like 500 or something like that. And that would almost look like a line. I know it doesn't look exactly like a line, but it would almost look very close to a line. In fact, if I zoomed in, this blue thing would look like a line, but we know that it's not a line. It's because we're too far zoomed in. As you zoom out, you can see the curve. But I guarantee you that that's still a parabola. In fact, if I zoom out enough, that red one will look like just a vertical line, whereas this blue one still looks like a regular parabola. In fact, the parabola that we're used to seeing. So that's me playing with the zoom button. I'm not changing the parabola per se, but I'm changing how I look at it as far as the scale goes. Oops, got off there for some reason. All right, let's zoom in just a little bit more. There we go. That would be perfect. Okay. Now if I slap on a negative out in front, we've already talked about this one before. This one takes that parabola and puts it on its head. I'm too lazy to write out the table, so I'll just show you what it looks like right here. It takes the blue parabola is exactly the red parabola, however, it's flipped upside down. Now if I put a negative 2x squared, alright, so if I put a 2 out in front, that takes the parabola and makes it skinnier or vertically stretches it. We already established that. But if I put a negative out in front, all that does is it's going to take that vertically stretched one and flip him upside down. Similarly, if I have a negative 1/2, well, first of all, the 1/2 makes the parabola fatter. If I take a negative and put it out in front, it's going to take an upside down negative or fatter parabola. So that would be all of the things this investigation wanted me to go through. Yep, that's it. Alright. How does the graph of the parent function change when a is negative? It takes that parabola and flips it upside down. Question 2. How does the graph of the parent function change as the magnitude of a is greater than 1? Well, it takes it and puts it on a slim fast plan, or also known as the vertically stretched torture test. Now, notice how they say the magnitude is greater than 1? Because that basically means if I have a 2 or a negative 2, that still stretches it vertically. The negative just flips it upside down. The magnitude of a is less than 1. Basically, if I'm dealing with a fraction here, then I'm taking this thing and putting it on the get chunky diet, which basically means I'm crushing the head and the bottom in between my fingers. I'm making this graph fatter. How do I think j of x equals 2x squared will be different from, or 3x squared compares to 2x squared? Well, 3 is bigger than 2, so I would say that it's going to vertically stretch it even more.